Okay, I can start, and my name is Sofia Konyukova, and today I want to present problem number 14, problem rising in the bulk. Let's remember the problem statement. We have vessel that's shaken appropriately, and if we place at the bottom some body, it will rising up. So we need to explain the phenomenon and create the device with the most energy efficient shaking technique. So sorry. Firstly, we need to create a vibration surface. We need to create a vibration surface for somehow. First, we need to create a vibration surface for first observations. It consists of a vessel fastening, vibration surface, springs, motor with eccentric, and cable. So you can see how it looks in real life. So after that, we need to clarify vibration. We need to clarify vibration type. We believe that it is sine signal, and for and we need to prove it. And we need to prove it. We use oscilloscope and Arduino accelerometer to understand what vibration type is that. So we can get closer image of it, and we need to understand is it sine or not. So we can make fast Fourier transform, and as we see only one mean peak, and it means that we have a sine signal with good accuracy. After that, we can make first observation of the process, and as you see, the ball rising. So the main point is to detect the position of the ball, and for that we use stick. We use stick, and we track stick coordinate, and also we need to limit the freedom degree and estimate stick influence of rising process on rising process. For that, we, as we see, the highest time measurement error is about 1 second, and it's extremely small for us. So you can see my outline. Firstly, we need to understand rising mechanism in one period of ball motion, and understand sand behavior in this one period. Of course, we need to quantitative explain it, and make the experimental proofs of it. So let's try to qualitative explain.
Excuse me, maybe just before you start, yeah, so just make sure to try and explain everything in about 7-8 minutes, so people can also then present. Did you understand me?
Okay. Okay.
Then you can have 1 or 2 questions. Okay, thanks.
So firstly, we need stable system, and then the vibration surface moves up. The sand and the ball start to move up too. So when the sand goes down with the system, with the vibration system under action of the friction force, but the ball moves up by inertia relative to the table. So after that, cavity under the ball forms, and we can see a cavity after cavity under balls falls. And as you can see, we see small cavity under the ball, but we can't see the second part because we have imperfections of 2D conditions. So then the sand particles starts to fill cavity space, to fill free cavity space, and the ball is stopped by the surface by the force of resistance of the sand, and it starts to fall. So the ball falls on the surface, and the important thing is that not all volume of the cavity is filling in the end of the process. So we can see experimentally that the cavity is filling during this process, and also we can see it from video. Our qualitative explanation is proved in article, and as you can see, the track motion of ball in one period is something like jump and fall. So it confirms our explanation. So we describe rising mechanism, and now we need to theoretically describe this. So we need to write Jensen's equation. It's about distribution of pressures in the sand. It exists because we have some weight distribution from upper particles to lower particles. We can write second Newton's law for it and calculate vertical pressure depending on coordinate. And as you can see, then we have external force and we have no external force. There is a difference about 5%, and we can assume that it is small error and small error. So we need to determine Jensen's coefficient. We need to determine Jensen's coefficient, and as you can see, the coefficient goes to a constant, but in solution we use interpolation for good accuracy. And on slide you can see how vertical pressure distribution changes. So after that, we need to describe horizontal forces, and also we can write second Newton's law for it and calculate horizontal pressure distributions, horizontal force distributions. And as you can see, radial force increases towards the walls, and it confirms it confirms our qualitative explanation. So after that, we need to go to quantitative part. We can write second Newton's law for our ball, and the ball trajectory is something like parabola. And after that, we need to calculate sand filling in cavity filling. For it, we write second Newton's law with filling coefficient. It's something like continuity equation. The calculation of its equation you can see on slide. So the intersection point is point where ball falls into the cavity, and after that balls move with vibration surface. And the ball trajectory is something like a combination of jumps. So after that, we need to experimentally prove our theory. So we can see good agreement of theory and experiment. Good agreement And we need to make some parametric investigation. You can see rising time depending on sand height. Also, we have good agreement, but in last part, we see something like big errors, and we can explain it another dimensional shaking effect. So the most important part of this work is plot a rising time depending on density. We can see three parts of the process. It's first part, it's about horizontal shaking. Second part, it's convection inhibition, and the third part is cavity filling. As you can see, cavity filling process is described. It has good agreement. So and also we need to create shaking technique optimization. Shaking technique optimization, the surface of the sand should catch up with the ball at the top of the lift, and at the top of the ball's rise, a new impact must occur. So we need to create a vibration table, something like that. And as you can see, theoretically, rising time in decreasing so much, and so it is our optimization. Thanks for your attention.
So I believe it's evening over there right now. So good evening from this side of the world. And my name is Saad. I'm from Pakistan, studying in University of Yas. So the problem I would be presenting is that I have to propose an experiment using Ollie camera and standard sensors of a smartphone to prove or disprove the flat Earth hypothesis. Using the same equipment, estimate the size of the Earth with as high accuracy as possible. So just a minute. So from the problem, we have taken the advantage to include GPS within the sensors of mobile. From that, we can get info about our longitude and latitude. We are assuming at this point that the Earth is spherical, so we are taking it as an assumption. So what we are trying to model is the time difference between the sunrise or sunset at location A and location B. That can be then matched with the experimental results or fitted with already available data to test the hypothesis. So to model our system, we are just simply starting with a sphere and a plane, cutting it in a half along the z-axis. This would be the north-south pole of Earth. On the other hand, we know that Earth spins at an angle of approximately 23.5 degrees from such an axis. So we change our reference frame to that coordinate system. So here the black line represents the axis of spin, which is at 23.5 degrees from our plane. Also is indicated the angle gamma that is associated with the revolution of Earth around the sun. So this changes from 0 to 360 as time passes throughout the year. So we just construct the equation of plane by plugging in 3 points in this determinant. These points are the origin, the 0,0 point, another point that is 0,0r along the z-axis point, where r is along the z-axis, and some point written as r sine gamma and r cos gamma. That's a general point. So solving this, we get an equation of this plane in the xyz coordinate system. Now we are changing our coordinate system to beta equal to minus 23.5 degrees, and the transformation is also very trivial. Notice that only x and z are changed to x dash and z dash. We are only moving in the xz, while y remains the same as can be seen in the diagram. In the next page, I will show you that has gone before this transformation is in plane of xz. So by using equation 2 and equation 1, we are getting this form of x dash in terms of x and z dash. So now we can use the equation of plane that we derived earlier, that is x equal to minus y tan gamma in the equation of x dash we just formed, and by using the fact that y dash equal to y in this transformation, we get the equation of blue plane that was shown earlier in tilted coordinate system that is at minus 23.5 degrees with the original one. Now we change the tilted Cartesian coordinate into spherical coordinates by these transformations. We are doing this as our inputs will be in the form of latitude displayed as epsilon over here and longitude that is displayed as psi over here. So by plugging in these transformations into our equations of plane in tilted coordinate system, we convert equation of plane into spherical coordinate with our z-axis pointing in the direction of spin axis of the Earth. So by plugging in some more constants just to clean up the expression, some more algebra is done to simplify the expression. And we can get an expression in the form of secant x that is shown at the end of the slide, where x is our longitude plus omega t, that is the additional angle that is covered by the Earth when it spins around its axis. So this is just what we desire to, what we desire to measure is not just x, because that won't have any sense, but delta x would give us the time difference at two different longitudes that we can then confirm by experiment. So rest is just putting up all the constants back to get the final seemingly complicated expression, which is not really complicated because most of these things are just constants. So just to make it neater, we wrote a code to calculate this stuff. And what this code would require is latitude and longitude of location A and time of the year. The reference set in our code is June 21st. So you have to count the number of days passed from June 21st to the day at which experiment is being done to get that angle gamma. So this is the code that is written in C language. And if anyone wants to test it later, they are more than welcome to do that. And from our experiments and data that was already available, the model that we have calculated really fits well. And the experiment we performed were by choosing two places in Pakistan, one near Islamabad, which is the capital of the country, and other near Balochistan. The time of sunrise was noted and difference was matched with that predicted from the model, and the result was accurate within the range of seconds. Unfortunately, this could not be shown over here because the time we had was very limited. Actually, we did the experiment when the IPT released the problems, so we really did not had the experimental stuff to put over here. But the errors were really very low, and this actually disproves the flat Earth hypothesis. And the errors were mainly in the experimental result that were due to fluctuations in temperature, height above sea level, and variation in temperature, and etc. and so on. So the next part would be presented by Muhammad Umar, and I would request Matthews to allow him to share his screen.
Now, since you have agreed that the Earth is spherical, now let's find what its radius is. So the procedure here is using that during the sunrise or sunset, shadow travel along the height of a building. And we have used the time required for the shadow to sweep a known height of a building to calculate the radius of the Earth. Here, for this procedure, let's suppose this is sun and this is Earth, and this is the shadow of the Earth. And if I want to find the equation for this shadow, this will form actually a cylinder. The shadow will form a cylinder, and this cylinder will I will write the equation of the cylinder in this white, which is x dash and y dash coordinate system, and then I will transform the coordinate system to this pink one. Actually, this pink one I would like to call it as an absolute frame of reference. Like this is the equation of the cylinder, and this is actually the shifted. In the shifted, the same equation of the cylinder in the shifted coordinate system. And then this is the point. Let's suppose this point is the bottom of the building, or maybe it could be at the top of the building. And the position of this point can be specified by phi, theta, and r. And since this point moves along this axis of rotation, which is actually tilted due to this absolute coordinate system, which I called it earlier. This point, as this point rotates, this actually is a function of time. So theta will change with time. So I want to find the position of point P first in spherical coordinate. Then I will translate that coordinate system into Cartesian coordinate, this red one. And finally, I will go from red coordinate system to this absolute coordinate system. These are actually the equations. This is actually the equation of the that point P, and this point P is first translated to this coordinate system through these equations, and later on to the final absolute coordinate systems. These equations. Now I have the position of point P in the x, y, and z. All three positions. I have the position of point P. these are the function of time, since this theta is a function of time. And I also have a equation of the cylinder in this absolute coordinate system. Now what happens, these points when the top or the bottom of the building intersects this cylinder, then these points become the part of that cylinder. So I will put x, y, and z from these equation into the equation of the cylinder, which form the shadow of the earth. So putting all these equations here, these x values of x, y, and z, and from the geometry you can see that phi is related to latitude with this relationship, and theta is a function of time, which will change like this. Putting all these expressions into the original equation will give us this long equation. Actually, this equation tells us the top. This equation first will be used for the top, like the bottom of the building, when the shadow sweeps through the bottom of the building. Then when we use, this is radius of earth, and then this is the height of the building. No, actually, this is actually the height from sea level. And this the same equation will be used, but r dash this time will be used as in addition, we will add the height of the building there too. So we will get two equations. We know we have now two equations, and the time
Excuse me?
difference between these equations.
Can you hear me?
Yeah.
I'm going to ask you to quickly finish because we have some,
Yeah.
some other presentations.
And finally, I have three equations there, and these three equations are implicit equations. We cannot solve it manually, so we will put these equations into MATLAB or Mathematica or somewhere else and show the results there. And these were equations we plot in the same equation was plotted in the Desmos with the height from the sea level as 540 and the height of the building in 110. There we see the time difference between the top and the bottom. So from this we get the radius of the earth within the 80 kilometer accuracy Actually, this equation that we drive are extremely generalized. We can use them for simulation. The angle can be tilted, and any angle can be used, and any part of the year can be used, and any location on the earth can be used. So these are extremely generalized equations. These maybe this is the part top of the building, and this is the bottom. As this rotates, this intersects, like as I said. In this way, we can calculate the radius of the earth, and the radius of the earth was within 80 kilometers of accuracy and certainty. So actually, we were using a mobile phone. So as this was sweeping, the rays of the sun was sweeping the building. So the luminosity was changing as we were making video. So this time is actually the time difference we use in the equation. So from this we also did an experiment that was in perfect agreement with all these calculations. And these are the references for the GeoGebra that simulation that we used, and the Desmos, the equation we plot there, and all other sources we can use there. If you have any question, you can ask.